Hello students, in this video I'll cover the last of the premium principles, which is called the risk-adjusted premium principle. Now let me just adjust this. No, that's too big. Okay, here we go. So risk-adjusted premium principle. Let's take the principle and then explain it and then check the properties. So now this, careful, it applies to a non-negative random variable. Okay, so we're in a context where we know that the random variable doesn't take negative values. Then we can apply or use this principle. So assume the CDF of the random variable is this. You have rho here is a parameter bigger than 1. The premium would be set like this. Take the integral from 0 to infinity of the probability x exceeds little x, but this probability is to the power of 1 over rho. Okay, and it's the integral for all x. Now notice, of course, this probability x is bigger than little x is just the survival function, 1 minus the CDF. Okay, that's how you set the premium. Now, why does it make sense? Let's explain. Well, in one sentence, what is this doing is actually quite similar to the Escher principle, at least conceptually. We're finding the expectation of a transformed version of x where the tail risk, so the probability of large values, has increased. Okay, can we see that with this formula? I think we can, but let's explain step by step. We're going to use the same strategy as with the Escher principle. We're going to find explicitly this transform variable of which we're taking the expectation. So bear with me. Consider this other random variable. Here we call it x star with the following CDF. Okay, the CDF of x star, let's denote it h. So the probability x star is smaller than whatever number little x. We define it to be 1 minus what we had over there. 1 minus the CDF of x. Okay, big F is the CDF of the regular or the initial x. You could have put an x here, big X. Okay, to the power of 1 over rho. Now, I actually don't put a proof here, but this, it's not especially hard to show it's a valid CDF. Okay, maybe you want to try to show this for yourself. To show this is a valid CDF, well, remember the properties of the CDF. The limit when x goes to infinity should be 1. The limit when x goes to minus infinity should be 0. And then it should be a non-decreasing function. That's quite easy to see. This would be a non-decreasing function. And also it needs to be right continuous. But you see, right continuous, big F is itself right continuous, okay, by definition, because it's a valid CDF. But now here, this, you can say it's some function of big F, but it's a continuous function of big F. So continuous function of a right continuous function will give you a right continuous function. Okay, now, hopefully you agree or you trust me that this is a valid CDF, H. Now, there's another property that I imagine you've seen before. If not, I'll make a tutorial exercise to verify that this is true. But you can find the expectation of any non-negative. So careful, this needs to be true, okay? Any non-negative x, you can find its expectation with this trick. Just take the integral on the whole support, so from 0 to infinity, of the survival function. Okay, that's always true for a non-negative random variable. Whether it's continuous or discrete or even mixed, this is true if the variable is non-negative. Okay, with this property, now we can see that the premium here is in fact just the expectation of x star. Well, yes. Expectation of x star, what would it be? Well, using this trick, it's just the integral from 0 to infinity of the survival function, 1 minus the CDF, of h star, which we defined to be, we constructed it to be this, okay? So, of course, 1 minus hx will give us 1 minus f to the 1 over rho. Okay, so this is just by how we constructed x star, this this is true. Okay, just by definition of what we made X star to be. But then we realize this exactly matches the premium under our premium principle. Okay, so again, as we said, this X star as a pure premium, okay, as expectation, equal to the premium under this risk-adjusted premium principle. But now notice the following. Why does this make sense to set the premium of X to be the pure premium of this transformed version of X, this X star? Well, X star is a version of X where the survival is greater. Okay, the chance of surviving up to any number little x is greater for X star. But you see, if the chance of surviving, by surviving, I mean the chance that X is greater than any little value, little x, if this is greater for X star, well, it means that our risk is more likely to be big, because at any threshold little x, the probability to exceed little x is larger for X star compared to X. Okay, so said otherwise, yes, this matches what we said here. The tail risk has increased because the probability to be big has increased for X star. Now, let's just explain. I think here I added something just to make sure we agree on this point, that X has a larger survival. Well, yes, because yeah, the survival function of X star is this. Okay, but I'm saying that this thing is larger than the survival function of the regular X. You can see this quite easily. I mean, you can see it. You know, you can try with your calculator. You know, if we go here, 1 minus f is a number smaller or equal to 1. You take a number smaller or equal to 1 to the power of something smaller or equal to 1 is going to increase the number. You know, take your calculator, 0.5, okay, to the power of whatever, 0.5, say, is going to be 0.7 something. So it's going to be bigger than 0.5, okay? 0.9 to the power of 0.6 is going to be bigger than 0.9. It's going to be 0.938. I don't know if you can see. Anyway, but okay, this, if you're not convinced, you can check this, that this works all the time. Meaning 1 minus fx to the 1 over rho. I want to let me find a color. I want to show that this is always bigger than 1 minus fx. Well, I add 1 and I subtract 1, so I haven't changed anything. But why do I do that? Well, then I can put 1 minus fx in front. Okay, and on the other side is left whatever is left over here, 1 minus fx to the power of 1 over rho plus minus 1, sorry. But then 1 minus fx, I can say it's you know, 1 divided by 1 minus fx to the power of minus 1. Okay, but then here, if I put the minus 1 or you know, a minus 1 here, it's going to reverse. Of course, it's going to be 1 minus 1 over rho. Okay, and then what happens? It happens that, you know, that this part, 1 over a number that's smaller or equal to 1 would be at least 1, so bigger or equal to 1. And then this thing, recall that rho is 1 or above. Okay, rho is bigger than 1. So 1 minus 1 over something bigger than 1, this whole thing is bigger than 0. Okay, so something bigger than 1 to the power of something that's bigger than 0, this whole thing is bigger than 1. Okay, so then we have proven the result, because well, what I started here with, I know, okay, those calculations show that this thing, 1 minus fx to the 1 over rho, okay, this is at least as big, okay, than 1 minus fx. Okay, because it is equal to 1 minus fx times something that's 1 or bigger. Okay, so I've shown what I want. the survival of X star is larger than the survival of X for every threshold. Yeah. Okay, and here we have a simple example. So if X is exponential, what would be the risk-adjusted premium for X? Okay, assume that rho is strictly bigger than 1. So here for the exponential, a bit like we had with the Escher principle, there's a very nice well, it's very simple, because you'll see you can first find what is the CDF of your X star. Well, by definition, its CDF is 1 minus, sorry, it's survival here. Okay, we can call this a S star, the survival function. Okay, it's 1 minus the CDF. CDF H is 1 minus F to the power of 1 over rho. But of course, you know that for the exponential, 1 minus fx would be just, well, just this, e to the minus lambda x. Of course, you take to the power of 1 over rho, you're going to get this. But you recognize that this is the survival function of a new exponential with parameter lambda divided by rho. And obviously, now why do we do this? Well, we know that the premium is just the expectation of this X star. So expectation of X star is easily found here. And you have, of course, rho divided by lambda. And recall, rho is strictly bigger than 1. So, of course, this is strictly bigger than the expectation of X, because the expectation of X is 1 over lambda. Okay, so that's easy example. Now, okay, a few more words of interpretation, then we're going to check the axioms, and I believe then we're going to be good. So if X, okay, for ease of interpretation, now let's assume that X is continuous. Now, here we have not assumed X was continuous. We just assume that X is non-negative. If we want to help our interpretation, we're just going to do a bit more work with assuming X is continuous. Use the chain rule to find the PDF of X star. Nothing is especially hard here. You just derivate big H as given before. Over here, derivate this with respect to X. You're going to get this in front and blah, blah, blah. Okay, you get this thing. So you see, it's this times the CDF of, the density of little x, the density of X. Okay, so you might write it as a certain weight, which is this blue thing, times the density of X. So you see, the density of X star, so H of X, is some modification of the density of X, okay, where you might call this weight W some risk adjustment. Okay, so you multiply the initial density by some value. So this weight makes each outcome X more or less likely compared to the initial X. So after the transformation, every outcome little x is more or less likely based on whatever the value of this weight. But this weight, you can easily see or show that it's increasing. It's an increasing function of X. Because if you derivate the weight, so you derivate this expression there, again, you're going to get the 1 rho minus 1 in front. Whoops. Here, and then there's going to be a minus that's going to be created by derivating 1 minus fx. Okay, you can check for yourself that you agree this expression is correct. But then this expression, see, it's strictly positive. It's strictly positive if rho is strictly bigger than 1, because then if rho is strictly bigger than 1 over rho is going to be smaller than 1. So then this is going to be negative. It's going to cancel the negative here, and everything else here is positive. Okay, so everything there is positive. So overall, yes, you have that this derivative is positive. The weight is an increasing function of X. So you can say a larger and larger weight is allocated to larger and larger outcomes of X. Okay, which of course represent larger losses. So again, we have a confirmation of what we said by analyzing the survival here. But you looking at the density under the transformation compared to the initial variable, the larger x's have a bigger weight, so it makes big losses more likely. So the x star is then riskier than the initial x. Okay, so you see conceptually it's quite similar to the Escher principle. We're charging a premium by putting a loading in the following way. We find an x star that is riskier than the initial x, and then we take the pure premium of this x star. But you see this is in fact loading the premium of x. Okay, because we pretend that the x is heavier tailed than what it really is by this transformation. Okay, then let's have a look at the axioms or desirable properties. Now, spoiler, risk-adjusted premium principle satisfies 4 out of 5. Okay, so non-negative loading, scale invariance, consistency, no ripoff. It does not satisfy additivity. Those are really simple to check, so let's go over them. Non-negative loading, well, this is immediate from the work we've done before. By definition, the premium is this, but we just said that this is larger than, well, than 1 minus fx. So you integrate something that's larger than this, so you have that the integral must be bigger. And what is this? Well, just the expectation of x. Scale invariance, you write what's the definition of the premium of a times x. By definition is this. Then you might rewrite it as x bigger than little z. Here we call it little z. Okay, integration with respect to little z as well. You rewrite it as z divided by little a. Recall here little a is positive. And then you can just make the simple change of variable, call little x to be z divided by a. So well, dz is then going to be a dx. Okay, so dz, you replace it by a dx. So you have a dx here and an a here. And then everything is fine. The integral went from 0 to infinity. That's still the case because a is positive. And you're done, because what's here, well, that's just the premium of x under the principle. You keep going. Consistency. What's the premium of x plus a constant? So recall c is a constant. So you would integrate the, well, okay, this is just by definition, probability that x plus the constant is bigger than y, and then you integrate with respect to y. Put it on the other side. Now, again, you can make a change of variable. X equals y minus c. Now dx equals dy, but here you do need to change the integration bound. Okay, if y was going from 0 to infinity, now x is going to go from 0 minus c, so from minus c to infinity. Now you just need to be a bit careful here. Probability that x is bigger than some little x, but here we start the integration at minus c. Well, for every x that's negative, so every x from minus c to 0, this probability is 1, because x, by definition, we assume it's non-negative. So the probability that x exceeds a negative number is 100%. Okay, so this is why we split this integral from minus c to 0, and then here we have a 1, and then on this side, easy, this side from 0 to infinity, blah blah blah, that's just the premium of x. Okay, and here of course the integral from minus c to 0 of 1 is just c, is just c. So we have what we want. And I guess, okay, well, I suppose here we assume c was positive. Okay, this to work. And then no ripoff, easy as well. Integrate from 0 to xm. That's the okay. Well, here, well, we use xm, which might be finite or infinity. But of course, this thing is smaller or equal to smaller or equal to 1. You take the power, it's still smaller or equal to 1. So then the integral would be smaller than if you replace this whole thing by 1. And of course, integral from 0 to xm of 1 will be xm. So yes, you've shown the no ripoff. Okay, and lastly, I've given you the spoiler already. Additivity is not verified. We can check this with an example, okay, or a counter example, meaning an example that disproves something. I think here we take the same simple setting as before. Let's have x1 and x2 be two Bernoulli and check if well, use this setting to show that the additivity property doesn't hold up. So you find a premium of x1 plus a premium of x2. You check that it's not equal to the premium of x1 plus x2 taken as a unique. Okay, you see this as its own unique random variable. Okay, so you show that this is not equal to the premium of x1 plus the premium of x2, but of course here they're identically distributed. So the premium of x1 plus the premium of x2 is also twice the premium of x1. Okay, so let's do that now. Here you could take any row, but let's just take row equals 2. Okay, it's a counterexample, so you can pick an infinity of counterexample. In fact, so arbitrarily we pick row equals 2. Now note what's the CDF of x, okay, or x1, but you see what I mean. Okay, at 0 it's 1/2, and at 1 it's 1. Okay, it's the step function. I put a plot here just to make sure. Okay, the CDF of x. Okay, the probability to be smaller than a negative number is 0, but then at 0, what's the probability to be smaller or equal to 0? Well, it jumps to 1, then it stays constant, and then at 1, see, at 1 it jumps to 1, because what's the probability to be smaller or equal to 1? Well, it's 100%. Okay, now to compute the premium, we take the integral, well, in the general formula is from 0 to infinity of 1 minus the CDF, but of course here, after 1, well, okay, we take 1 minus the CDF. Okay, 1 minus the CDF, or 1 minus the CDF will be, it's 1 before 0, and then at 0 it's 1/2. Okay, and then from 1 it's 0. So in fact, we're just integrating this part. Okay, so we're integrating from 0 to infinity. Here I said we pick row equals 2, so we take the square root. So remember, it's 1 over row, so the square root in this case of 1 minus fx, but 1 minus fx from 0 to 1 is 1/2. Okay, so you get the square root of 1/2. That's for the premium of 1. Okay, the pi of x1. Now we find a premium of their sum. That their sum is a binomial with number of trials 2 and probability of success 1/2. So again, easy to find the CDF. Okay, at 0 it's, so this is the right part here. At 0, or before 0 it's 0, and then at 0 exactly it jumps to 1/4, because the probability that the binomial 2 1/2 equals 0, it's 1/4, and then at 1 it jumps to 3/4. Okay, because the probability of binomial is smaller or equal to 1, with probability it's 0 plus the probability it's 1, which is 1/4 plus 1/2, it's 3/4, and then etc. Okay, at 2 it jumps to 1. Okay, so the 1 minus the CDF or the survival is the opposite. Okay, it's 1 here, and then at 0 it jumps down to 3/4, and then at 1 it jumps down to 1/4. Okay, and this we use to find the premium, which is then the integral from 0 to 1 of the square root of 3/4 plus integral from 1 to 2 of the square root of 1/4. Okay, so it's the area under the curve here, and the area under the curve here. Well, not okay. Why? This is not really the area under the curve, but you see what I mean, right? You integrate because the function is the square root, right? But then you get square root of 3/4 plus square root of 0.25, and you can compute this. It's obviously not equal, right? The square root of 3/4 square root of 1/4 is not twice the square root of 1/2. So yes, indeed, additivity doesn't hold up for this principle. So basically, we get maybe slightly unsatisfying final words, which is that none of those principles satisfy all 5 axioms aside the pure premium. But we also said that the pure premium is not tenable in practice because you don't have any safety. And yes, that's one of the slides. So I'll stop the video here, and thanks so much for listening as usual. I'll catch you in the next video or in the lecture. And if you watch this before the test, good luck for the test.